Take a look inside almost any electronic device, your phone, your laptop, a microwave, a car, and you'll find the same thing, a flat green board covered in a maze of tiny metallic lines. This is the printed circuit board, and it is the unsung foundation of the entire modern world. Billions of them are manufactured every year. Without it, there would be no computers, no smartphones, no internet, none of the technology we depend on every single day. But how do you actually build one of these intricate green boards, packed with thousands of microscopic connections that never touch when they shouldn't? The process is a fascinating blend of chemistry, precision lasers, robotics, and even a thin layer of real gold. Today we're going inside the factory to find out exactly how circuit boards are made. The circuit board was born out of necessity. Before it existed, electronics were wired by hand, a tangled, fragile mess of individual wires soldered point to point, bulky and prone to failure. Then, in the 1930s, an Austrian engineer named Paul Eisler had a better idea. Instead of wires, why not print the connections directly onto a board, like ink on paper? Eisler built his first working printed circuit inside a radio in 1943. His invention got its first big break during the Second World War, when the United States used printed circuits in the proximity fuse, a top-secret, radar-triggered artillery shell so important it was said to rank second only to the atomic bomb. Yet Eisler wasn't formally recognized as the inventor until 1971. Today, his idea sits inside nearly every device you own. So what exactly is a circuit board? At its heart is the substrate, a rigid, non-conductive sheet that everything is built upon. The most common material is called FR4, layers of woven fiberglass bonded together with epoxy resin, making it strong, heat-resistant, and electrically insulating. Bonded to that substrate is a thin layer of copper, the metal that actually carries the electricity. The entire manufacturing process is really about one thing: carving that solid sheet of copper into a precise pattern of pathways, called traces, that guide electricity exactly where it needs to go. Complex boards stack multiple copper layers, separated by insulation, with tiny plated holes called vias connecting them. A single modern board can hold dozens of layers, all working together in a space thinner than a small stack of coins. Every circuit board begins not in a factory, but on a computer screen. Engineers first draw a schematic, a diagram showing every component and how they connect electrically. Then that schematic is translated into a physical layout, mapping the exact position of every trace, pad, and hole across each layer of the board. This is a painstaking puzzle. Thousands of connections have to be routed without ever crossing on the same layer, like a subway map with no accidental intersections. When the design is finished, it's exported into a set of files that describe the board layer by layer. These files are the master blueprint. They're sent to the factory, where machines will follow them precisely to bring the design to life in copper and fiberglass. Manufacturing begins with the raw material, a copper-clad laminate. This is a sheet of that FR4 fiberglass substrate with a thin foil of copper pressed onto one or both sides under intense heat and pressure. At this stage, the entire surface is covered in solid copper, a blank canvas. The goal now is to remove all of that copper except the precise pattern of traces the design calls for. The board is first cleaned thoroughly because even a speck of dust or a fingerprint could ruin the delicate pattern to come. Then it's coated with a light-sensitive chemical called photoresist, a film that hardens when exposed to ultraviolet light. This coating is the key to transferring the design onto the copper, and it sets up one of the most elegant steps in the entire process. This step borrows a technique from photography. The board, now coated in light-sensitive photoresist, is covered with the circuit pattern from the design files. Powerful ultraviolet light is then shown onto the board. Wherever the light strikes, the photoresist hardens. Wherever the pattern blocks the light, it stays soft. The board is then washed in a developer solution that rinses away only the soft, unexposed resist. What remains is a perfect, hardened stencil of the circuit, protecting the copper that needs to survive and leaving the rest exposed. In effect, the factory has just printed an invisible map onto the board, one that tells the next stage exactly which copper to keep and which to destroy. It's precise enough to define lines far thinner than a human hair. Now comes the moment the board truly takes shape: etching. The board is passed through a powerful chemical bath, often containing a solution like ferric chloride. This chemical dissolves copper, but only the exposed copper. The areas protected by the hardened photoresist are left untouched. As the unwanted copper washes away, the circuit pattern finally emerges. A gleaming network of copper traces standing exactly where the design intended. This is called a subtractive process because the board is created by taking material away, like a sculptor chiseling a statue from a block of stone. Once etching is complete, the protective photoresist has done its job, and it's stripped off, revealing the bare copper circuitry beneath. For a simple single-layer board, the wiring is now essentially done. But most modern boards are far more complex. Most circuit boards aren't a single layer. They're many, stacked like a sandwich. A smartphone board might contain 10, 12, or even more layers of circuitry packed into a sliver of space. To build these, each inner layer is etched separately, then carefully aligned, a process where being off by even a fraction of a millimeter can ruin the entire board. The layers are interleaved with sheets of a sticky, uncured fiberglass material, then pressed together in a lamination press under enormous heat and pressure. The heat melts the resin, which flows between the layers and then hardens, fusing everything into one solid, permanent block. What went in as separate thin sheets comes out as a single, unified board, with intricate copper circuitry now buried invisibly inside it. With the layers fused together, the board needs holes, lots of them. These holes serve two purposes: mounting points for components, and vias, the tiny vertical tunnels that connect the different copper layers to one another. Drilling is done by computer-controlled machines spinning drill bits at incredible speeds, up to hundreds of thousands of rotations per minute. Some holes are astonishingly small, as narrow as 0.2 of a millimeter, finer than the tip of a needle. A single complex board can require tens of thousands of these holes, each one placed in exactly the right spot according to the design files. And for the very smallest holes, factories don't use drill bits at all. They use precision lasers, capable of vaporizing openings far too tiny for any mechanical bit to reach. Here's a puzzle. Those freshly drilled holes have bare, non-conductive fiberglass walls. So how do they connect the copper layers above and below? The answer is plating. The entire board is run through a series of chemical baths that deposit a thin, even layer of copper across every surface, including the inside walls of every single hole. This transforms each drilled hole into a via, a conductive tube that electrically links the layers, allowing signals to travel up and down through the board, not just across it. It's this three-dimensional web of connections that gives modern circuit boards their incredible density and power. After plating, a second round of imaging and etching defines the final outer layer circuitry, completing the copper architecture of the entire board. Now the board finally gets its iconic look. A protective layer called solder mask is applied over the entire surface, coating and sealing the delicate copper traces. This mask insulates the circuitry, prevents corrosion, and stops solder from bridging across traces where it shouldn't during assembly. And this is where that famous color comes from, because solder mask is traditionally green. There's no single reason it became the standard. It's partly historical, and partly because green offers excellent contrast, making it easy for both machines and human inspectors to spot the tiniest defects. Though today you'll find boards in blue, red, black, and white, green remains the classic. After the mask, a printer adds the silkscreen, the white letters and numbers that label components and guide the people and machines that will assemble the board. Look closely at a finished circuit board, and you'll notice the exposed metal pads have a shiny, golden sheen. That's not just for looks. Bare copper, left exposed, would quickly oxidize and become difficult to solder. So the exposed pads are coated with a protective surface finish. One of the highest quality methods plates the pads with a thin layer of nickel and then covers that with a microscopically thin layer of real gold. Gold doesn't tarnish or corrode, so it keeps those critical contact points perfectly clean and solderable, sometimes for years. It's only a tiny amount of gold per board, but multiplied across the billions of boards made each year, the electronics industry is one of the largest consumers of gold on the entire planet. With the surface finish applied, the bare board is essentially complete. But a bare board is just an empty stage. To become useful, it needs its components, the chips, resistors, and capacitors that actually do the work. This stage is called assembly. First, a thin metal stencil is laid over the board, and solder paste, a gray mixture of tiny solder particles in sticky flux, is spread across it, depositing precise dabs onto every pad. Next comes the star of the show, the pick-and-place machine. This robotic marvel picks up components, some smaller than a grain of sand, and sets them onto the board with astonishing speed and accuracy, positioning tens of thousands of parts per hour. The board then travels through a reflow oven, which heats it until the solder paste melts and then solidifies, permanently bonding every component in place in a single pass. There's one final, crucial step: testing. A single faulty connection can render an entire board useless, so nothing ships without inspection. Automated optical cameras scan every board, comparing it against the original design to catch misaligned or missing parts. Electrical testers then probe the connections, confirming that every signal path works exactly as intended. Only then is the board approved. And here are a few things to appreciate the next time you crack open a gadget. That green board may hold miles of copper wiring compressed into a few square inches. It contains real gold, and it was built through dozens of precise chemical, mechanical, and robotic steps, all to guide invisible electricity along exactly the right path. From a hand-wired radio in the 1940s to the brain of every device today, that's how circuit boards are made. If you enjoyed this, subscribe. We break down how everyday things are made every single week. And tell us in the comments, what should we cover next?